Okay, I guess we are now ready to move to a presentation by the industry on the nuclear safety enhancement as outlined in CMD 14M54. This is a joint submission from OPG, Bruce Power, and NB Power. I understand that Ms. Powers will make the presentation. The floor is yours. You want to...
President of Engineering Strategy at Ontario Power Generation. Good day, and thank you for the opportunity to speak to you today. I am speaking on behalf of the industry. My colleagues at Bruce Power in New Brunswick Power will assist as required. Our objective today is to update the Commission on the progress of the nuclear safety enhancements the utilities have been implementing based on the lessons learned since the Fukushima event. Canadian nuclear utilities have continued to make progress on the implementation of lessons learned from the Fukushima event. Today, we will update you on our work covering CNSC Fukushima Action Item Closure Status, the progress on nuclear safety enhancements at the stations, emergency preparedness enhancements, human and organizational performance, and industry interaction and leadership. In February 2012, the CNSC issued the Fukushima Action Items, or FAIs, to each of the nuclear utilities in Canada. This table represents the current status of the Fukushima Action Items for each of the utilities. As you can see, industry has made good progress in addressing the CNSC FAIs, and we are on track for requesting closure of the remaining FAIs to meet the CNSC schedule. In some cases, the CNSC has also issued station-specific action items to track the implementation of modifications resulting from the closed FAIs. We approached the lessons learned from Fukushima in a systematic way, guided by the CNSC and national and international common strategies. The industry is conducting evaluations of the potential external hazards at our plants, design basis and beyond design basis. While we recognized that our plants were safe, improvements could be made to be able to respond in the extremely unlikely event that all of our installed backup equipment is not available. Therefore, we have added portable emergency mitigating equipment, pumps and generators, to add an additional layer of defense. This installed equipment gives us the capability for portable pumps to add water to the boilers, irradiated fuel bays, heat transport and moderator systems to cool the core, or portable electrical supplies to repower critical instrumentation in the event of a beyond design basis accident. We are adding more equipment to enhance our capability and are installing quick connects to streamline the deployment of the portable equipment and enhance containment protection. Severe accident management guidelines have been issued at all of the Canadian nuclear stations, and these provide flexible guidelines to be able to respond to extreme events. We have implemented measures to limit and mitigate the effects of hydrogen buildup under accident conditions. And we are enhancing our ability to ensure containment integrity through containment venting provisions. We have confirmed bleed degasser relief valve capability and have evaluated shield tank overprotection relief, the outcome of which we are making plant modifications where appropriate to ensure this important core cooling provision is retained. Emergency preparedness enhancements are continuing, including both on and off-site provisions. As well, our communication improvements, such as satellite and deployable radio communications are being installed at our sites. These enhancements represent major resource commitments and cost expenditures for the Canadian utilities. From an OPG perspective, we have currently spent over $70 million on the work conducted to date, and we expect to spend a total of about $200 million by the time the projects are completed. We are also spending additional funds on the safety improvements planned as part of the Darlington refurbishment project, including major items such as the new containment filtered venting system at Darlington. Our portable pumps include a mix of trailer-mounted pumps and fire trucks. This emergency mitigating water can be fed to multiple locations: boilers, heat transport, and moderator for core cooling, and irradiated fuel bay cooling if the normal and backup supplies are unavailable. To enable rapid deployment and connection to station systems for core cooling, we are installing quick connect fittings on our systems, as shown in the example on the upper right photographs. Our portable generators provide power to key instrumentation and systems. They are stored at the site, but separate from the station equipment, and can be deployed in the event of an accident. With these two, we are installing quick connect electrical fittings to improve deployment time over the currently installed configurations. All of the utilities are looking at providing further defense in depth by repowering additional station systems required in the long run. All licensees have installed passive autocatalytic recombiners, PAR, units within containment at their sites. OPG and New Brunswick Power have completed the installation of PARs in their units, and Bruce Power has completed PARs installation in all of their operating units, and they have some additional PARs yet to be installed in Unit 0 at Bruce A and Bruce B, and these will be installed per their outage schedule. We have confirmed through severe accident analysis that the hydrogen is controlled to acceptable levels when applied in conjunction with the in-vessel strategy developed by the utilities. PARs limit potential hydrogen buildup following an accident, and they require no power to operate. Containment integrity is preserved either through the installation of new venting systems. The Point LePro containment filtered venting system is shown here on the left, or through utilization or repowering of the existing venting systems, such as the emergency filtered air discharge system, or the Pickering FADS, is shown here on the right. Containment pressure control and cooling is also preserved through SAMG actions, and for some sites, through repowering containment air cooling units. All of the improvements we are placing in service are being tested through training and emergency preparedness drills and major exercises. Bruce Power conducted a major exercise, the Huron Challenge, in September of 2012 with over 50 organizations participating. In May of this year, OPG completed Canada's largest nuclear emergency exercise with more than 1,000 participants from 54 federal, provincial, and municipal agencies. The primary objective of this exercise was to assess the integration of nuclear emergency plans for those agencies that would be required to respond in the event of an accident. OPG is planning to return to a CNSC meeting in November of this year to provide the Commission with an overview of our findings. At all sites, emergency mitigating equipment drills and severe accident management drills are being added to the drill program. I mentioned two major exercises being complete, the Huron Challenge at Bruce, and Exercise Unified Response at OPG Darlington. But further drills are planned with a Beyond Design Basis drill at Pickering scheduled for the fall of 2014. And a major exercise at Point Lepreau, Exercise Intrepid 2015, which is planned for November 2015. Mutual aid agreements and external support agreements are in place to expedite the ability of the utilities to exchange equipment and resources if a beyond design basis accident were to occur. Multi-unit severe accident drills will be conducted in 2015 to validate further enhancements being made to severe accident management guidelines. OPG and Bruce Power have also established automatic near-boundary radiation monitoring, and New Brunswick Power is in the process on a similar design. Bruce Power has transitioned to an enhanced emergency response program and established a new emergency management center. New Brunswick Power is in the progress of building a new off-site emergency response center. And all sites are making further communication system enhancements to aid in emergency response. Human and organizational performance aspects have been built into all of the work programs. We have conducted human factor reviews of exercises, drills, and supporting plant modifications, as well as assessments on the habitability of control facilities were conducted as part of the work under FAI 1.9.1. Emergency radiological exposure planning is being examined and streamlined where necessary, and we continue to make improvements to enhance the realism of our drills and exercises. We have also recognized the importance of decision-making processes as we transition from a design basis scenario to a beyond design basis. In such cases, we transfer from rule-based operating regime to a knowledge-based response, basically from procedures to guidelines. Three elements feed into the prioritization and decision-making process that must be used as we make this transition: critical thinking, a bias towards action, and the authority to act. We are continuing to work with leadership at the stations to ensure that we provide opportunities for them to practice and discuss this important aspect of accident response. We have developed and are continuing to support this with tools, training, and exercises. Our experience has been that staff are very receptive, and they've been providing us with suggestions for further enhancements, which we are implementing. The Canadian nuclear utilities are providing important inputs to the continuing evolution of practices and regulations, building on the lessons learned. CANDU Industry Integration Team, or the CIIT, which is coordinated through the CANDU Owners Group. This team facilitates working closely domestically and with our international CANDU partners and gain from their perspective. We have conducted benchmarking visits and assessments to capture OPEX and lessons learned. The utilities work together to document the Canadian Nuclear Utility Principle for Beyond Design Basis events, signed by the Chief Nuclear Officers from the three nuclear utilities. This document was issued in August 2013 and describes a set of principles to which to define a common approach for a response to beyond design basis event. Industry has also provided input to the CNSC on the Fukushima omnibus updates to the Canadian nuclear regulatory documents and the related IAEA documents. Industry is also contributing with the CNSC to the development of new CSA standards related to accident response. We are also continuing to build upon our integration with INPO Nuclear Event Response Framework. This concludes our presentation. So for myself, on behalf of OPG Bruce Power and New Brunswick Power, thank you for giving us the opportunity to provide the update. And Frank, do you have some words to say?
Yeah, a few thoughts and a video for you here in a second on conclusion. One of the challenges with the Fukushima response, I think, is it's been a fairly highly technical discussion, both between us and CNSC, and trying to communicate to others who aren't directly involved in our industry what we're doing and what difference it really makes. Has not been simple. Huron Challenge was a major milestone for us. It was certainly, at the very least, an effort to communicate with public agencies and others about the changes we made and to test out our assumptions. And then we broke the Fukushima response into a phase 1 and a phase 2, phase 1 being all those activities which are aimed at preventing an event in the first place, which is, of course, by far the best way to protect the public is not to have an event, and phase 2, which is the attempt to truncate or limit an event should it occur. And since the completion of phase 1 at the end of last year, we've been focusing more on how we're going to tell this story and how we're going to let people see what we've done in practical terms. And if you bear with me for a few minutes, I'm going to attempt to play this video, which is now on the Bruce Power website. It's trying to show people in kind of more plain language the actual changes we've made, and you'll see in the video, for example, how we hook up some of these connections and so forth, which hopefully kind of clarifies it to people and takes some of the mystery out of it. The technical language sounds a lot more mysterious than the practical application in the field. So let's see if I can actually work the system here. Not enough traction for the mouse. Okay, so here's the video, I think. How do I do full screen here? This one? Not quite, no. That didn't quite work. What am I missing? Control F. You got it. Control F. There you go. Only need a little help with the technical stuff.
One of the considerations with natural disasters is their kind of unplanned nature. Fukushima was an extreme weather event. The site at Fukushima was consequently damaged because of their inability to cool fuel after the event occurred. Nuclear plants are already well designed and they have many redundant systems for any kind of conceivable event that can occur. So the question then is, what went wrong at Fukushima and why?
Everything worked properly until the actual tsunami hit. That then took away that supplementary power. It also flooded the basement, which had a lot of switchgear and critical equipment in it, which then precluded them from getting backup power back into the plant.
The biggest thing for us immediately after Fukushima was to go and look at our own defenses in the event of severe weather. Obviously, a tsunami off Lake Huron is very doubtful, but a tornado or a bad winter storm is not.
Based on Fukushima, then, we took a number of actions. We ran what we call a probabilistic safety analysis, looking at what could be possible and what could not. What if you missed something? What if an event that you didn't think was going to happen happened? What impact would that have? And how would you be certain that you could respond to it? The can-do design is, of course, very robust and has been proven over many years. However, it still seemed prudent to add extra layers of defense. So the first step was, in fact, to make some modifications internal to the plant to add some extra connection points that we could use to add the extra cooling water and the electricity. The second point was to develop a means of deploying equipment that would actually provide the water.
By design, the can-do system has two safety systems. Each are independent and diverse. So if one happens to fail, the other one would be available. Of course, we keep both systems healthy and active and poised and ready to go.
Shutdown system 1, for example, on a loss of power, all the rods go in. And on shutdown system 2, on a loss of air, all the poison goes in. So they're fail-safe systems that don't require operator intervention to fail in the event of a parameter trip. That's a key difference where operator action is required to actuate those safety systems. For every single accident that's been diagnosed by our safety analysis folks, there are 4 different trip parameters that could take that down, 2 on each shutdown system. So there's a ton of redundancy to take a unit offline based on any accident that can be postulated by our safety analysis group.
We have existing standby generators and emergency power generators that are part of the plant design. There are also other backup power systems.
We have diesel generators that back up our Class 3, and then we have other diesel generators that back up our qualified power supply. And we realized that if we lost all of our fuel tanks, we needed another backup.
They're in place to make sure that if we have a loss of Class 4 power or other power losses, that power still gets to the critical parts of the plant.
We also have emergency water. It comes to the station, connects to the emergency boiler cooling piping, and it can supply any unit.
So we store that in a place where it would be remote from the actual plant. So if you have an event at the plant, and as we drilled during the Huron Challenge, we simulated a Godrich-style F3 tornado working its way through the site. Because that equipment is held separately, it's not going to be damaged as a result of the natural disaster scenario. If that storage facility were to be hit, it's very unlikely that the plants would also suffer the same fate.
So there's new equipment, but more importantly, everyone's trained in how to use it.
We've developed a new off-site monitoring system out to 10 kilometers, which will automatically detect any radiation released. And in fact, it'll operate 24/7, whether there's a vent on or not. But this will provide very accurate and detailed tracking of any radiation that might be released in an emergency, thereby allowing the government to easily move people out of the way.
What this system does is it helps augment our current system that we have in place in terms of TLD chips. So we do have approximately 105 TLD chips within the 10-kilometer primary zone around the site. That provides us a very deep spectrum of any radionuclide, so the sensitivity of these detectors is quite amazing. Since Fukushima, Bruce Power has, we've done a lot of work in this area in terms of public notification. We're looking at expanding upon what we currently use in terms of telephone call-outs and sirens and these sorts of things to local FM radio stations. We've looked at pushing that same message through a local cable TV as well. We've discussed with Environment Canada the use of broadening that to include marine radio. Also are working towards cellular SMS texting. So we're looking at expanding into a more robust system that not only provides a signal but also a message to people so that they know what to do. We designed, developed, and implemented and delivered new training to a new 5-crew approach at Bruce Power that we're incorporating or looking at the use of tabletop exercises to keep crews engaged, as well as self-directed learning and these sorts of things.
In Huron Challenge, we considered things like tornadoes and earthquakes, and we have the equipment which can fill in holes or move trees or cars or anything that's blocking the road. We have more than one way of pulling water out of the lake, so that we're reasonably comfortable that that will work.
Our program for the Fukushima event, really a simple concept. We're taking everyday pieces of emergency response equipment, such as fire trucks, and we've trained our staff to be able to deploy them in an unconventional method. So really, instead of fighting fire, we're making connections that are hard piping onto the stations themselves to provide cooling in a very timely fashion to be able to ensure that the reactor cores remain cool and the fuel bays remain covered with water. Bruce Power undertook to rebuild the fire training facility, which was closed down a number of years ago. Every display that was incorporated into the design of this facility is all deemed to be a risk to a nuclear facility. The design of this facility is somewhat unique. We are going to have the capabilities to have live fire training 365 days of the year.
Bruce Power spends a lot of money and time training certified staff, and all its staff for that matter, to the point where you understand the theory and the design of the systems, not just the operation.
Well, the incident management system consolidates our emergency response approach into one command center. It enhances the coordination, communication.
So if there was a fire alarm within the station, There is a call that goes out to the Emergency Protective Services Organization. The Emergency Protective Services Organization are then tasked to provide response capabilities for both power as well as water supply through the fire trucks. We respond to the station and provide the water and power as needed.
It allows us to respond basically to an all hazards approach to any hazard that we could experience on site.
IMS is the system that's used for management in Ontario. It's adapted by the province and all the provincial agencies. So this allows us all to work together seamlessly. We feel that we've taken the Fukushima events very seriously, applied the lessons actually in a much broader sense than we would have applied in Fukushima, looking at not just those kind of events, but just any kind of event that might occur. We think our crews are well trained, they're on standby 24/7. So we feel that we have the capability in place to deal with virtually any emergency that will come our way. We certainly invite you to drop by our visitor center and have a closer look at the plant and the site and the facilities here. And I think you too will walk away with a level of confidence that the place is well looked after and we're well prepared.
But that's the intent for our public information. So it's on display now at our visitor center and it's on the website. A little bit long, but we wanted to kind of talk people through the process. So hopefully it was effective. And now turn it over to Paul at Point Lepreau.
Thank you. For the record, Paul Thompson, Manager of Performance Improvement and Regulatory Affairs at the Point Lepreau Generating Station. MB Power has expended considerable resources in the area of understanding and being prepared for severe accidents. This started as part of our life extension activities integrated into our refurbishment project, which put us in good stead prior to the accident at Fukushima Daiichi. And since then, again, in collaboration with our other nuclear Canadian partners, a lot of activities since the accident at Fukushima. I agree with Mr. Saunders that this is a very difficult subject area because it's quite highly technical, and quite often in trying to address some of these accidents and discussing the phenomenology and how we respond to them, it is a very confusing and challenging subject area. So I think this is a great video, Frank, and I think it really does help. We've used the trying to get the message across, which we firmly believe that we at Point Lepreau were safe leading into refurbishment. We were safer as a result of the activities we did for life extension and refurbishing the unit, and we're even more safe as a result of the additional enhancements we did as a result of the accident at Fukushima. And it's another way of saying the same thing, but it is a difficult challenge for us to try to get the message across on a very technical subject. So thank you, Frank. I think that was a great way to do that. Thank you.
Okay, thank you. Thank you for this.